So you know that for a bar, our symbolic stiffness matrix is K equal to EA all over L, 1 minus 1 minus 1, 1. Yes? So this is our target. You know that your finite element is equal to F equal to K multiplied by U. So for a bar, we know that this K is equal to this one here. But I think we're far off because at the moment what we know is that K is equal to the integral of that BE B transpose dV. So this is what we know at the moment. But what we know also is, of course, dV is equal to a dx, right? So this is one thing that we know later that we can substitute here when we take the line integral. The thing is, we're still unsure what to do with that v. Yeah. So we have this equation K equal to the volume integral v e v p dv. So let's have a look now. The thing that you have to do now here is to do a mapping from 0 to L, x1 to x2, to C1 to C2, or C1 to C2. So what's going to happen is that you're going to map. So mapping means from this one here, x1, x2, where you have here a leg L, will be mapped to this one here, wherein you have now here C1, which is minus 1, and then you have here C2, which is plus 1. And in the middle here will be 0. So that will be 0 there. So that's what we're going to do, wherein initially our axis is x, so this one our axis is now c. Now if we're going to interpolate, what will happen at any point x here, say x minus x1, and then that is x2 minus x1, so at any point. So this will be equal, corresponding to this one will be that c minus c1, c2 minus c1. Yes? But this one is c minus c1. C1 is negative 1. And then C2 is 1 minus a minus 1. So now you have now this one to be C plus 1 over 2. Yeah? Or 1 plus C. And then you can now simplify this one if you want to, such that you're going to solve for x. So we can now divide this one and solve this one here now. We have here x minus x1 equal to 1 plus c divided by 2 multiplied by x2 minus x1. And since we're interested with x, being the unknown parameter, we can now simplify this one to be x1 minus 1 plus c divided by 2 multiplied by x1 plus 1 plus c divided by 2 multiplied by x2. Yes? So this one now, if I'm one now will be x equal to n1 again, which is your geometric shape function, x1 plus n2 x2. Okay? Wherein you have n1 to be equal to 1 half 1 minus c, and then you have your n2 equal to 1 half 1 plus c. Yeah? So what to do next? We know that b is derivative of, again, recall, what is b? b is dn dx. Yes? b is dn dx. That's right. How to do that? What is n? d is equal to dn dx. How do we do that? We know that. Let's try n1. b1 is equal to dn1 dx. So let's try to substitute. That's d dx of 1 half 1 minus c. So it's going to be 0, yeah? So that is c, that is x. So what do we do? So this is the time that we introduce a term, Jacobian. So we're going to introduce a term, so that's the question there. We introduce a term, Jacobian, where this Jacobian, j, is equal to dx dc. Okay? But there will also be a value for this one later, I'll explain later. So we introduce the Jacobian here. So as you can see, we have now here d1 dn1 dx. We don't know how to move on because we got this shape function to be 1 half 1 minus c. N2 is equal to 1 half 1 plus c. But if we take the derivative with respect to x, it will be a problem. Because you're taking the derivative of this term, which is a function of c, taking the derivative with respect to x. We don't know that. So we need to introduce a term, Jacobian, which is dx dc. The value is L over 2. I'll just explain later why. So, what we're going to do now, so from here, so we have b equal to dn dx. By chain rule, we can have this one to be dn. Take a seat. Yes. Take a seat. Yes. And then this one is the inverse of your Jacobian. Now let's start to solve for this one first. Your Jacobian. Jacobian is equal to dx dc, or this can be delta x delta c. We can have the mapping. So again, we have this one here. From the mapping, we have this one to be x1, x2, and we have this one to be the length. And then this one will be c1 equal to -1, then we have c2 equal to this one will be the C2 minus the C1. And then x2 minus x1 is equal to the length. The C2, 1 minus a minus 1. So this one is L all over 2. So we have now this value. So this now is the next value that we need to solve for. Okay? So just a bit more energy. We're going to get there. Don't worry. Relax. It's going to end up soon. So here we go. It's going to end up soon. So we have d to c dx. We have now this value here because that is simply 2 over L. So this is not anymore our concern. Our concern will be dn d to c. So that's 1 all over j, right? So that's just 1 all over j. Don't put in the value first. It's just 1 all over j. You have dn1, dn2 with respect to the c. Yes? So have a look. So if I have now this one here, I have my d to c dx, dn d to c. So this one is simply your 1 over the Jacobian. And then this one is 1 over j. So what do we have here? So you have your n1 and 2. And then I would like to move here further. Sorry for that. Just put it here. 1 over j, d to c. What are my values? So I have dn1 is 1/2 1 minus the c. And then I have 1/2 1 plus the c. So getting better now, I hope. So that this one now is 1 all over j. Derivative of 1/2 multiplied by 1 minus the c with respect to the c. What is that? So this one is negative 1 multiplied by 1/2. That will be negative 1/2. Yes? And then derivative of 1/2 1 plus the c divided with respect to the c. That will now be 1/2. Yeah? So that is c. So c or c doesn't matter. So, are you okay? Getting there, right? Now let's move. Let's move on. We have now your D. So let's move on. Have a look at this one here. We have now your A equal to the volume integral. We got this one already. VE B transpose. Yes? That is dV. Let's put in values here. I'm just going to bring out E. So we have the volume integral, that's E. And then I'll put in this B here. So what is our B? That's 1 all over J. Minus 1/2, and this one is 1/2. So I'm bringing this one here. And then I have now this one here. So this one is a 2 by 1, this one is a 1 by 2. So definitely we're going to get a 2 by 2 here. So that is minus 1/2, and that's 1/2. We forgot the 1 over J there. And then I have my dV. Good? 1/4 minus 1/4 and then 1/4. Well, getting better. dv. Yes? What else? So, what's going to happen now, okay, is to integrate. But we know that dv is equal to ADX. But for some reason, we need to convert it to, since we have J here, we're not going to substitute the values first. Or we need to convert everything first to C. So we don't integrate with respect to dx, we integrate with respect to d to c. So let's have a look. So we have now here, this one here, so quite clear, it's getting a form now. We had now earlier, we discussed this one is ADX. Yeah. So now it's going to be the line integral rather than the volume integral. So if we want to simplify this one now, K is equal to your line integral E1 all over your Jacobian squared, 1/4 minus 1/4. So I'm just writing now, this one will be A dx. So I'm going to put everything so that we have now here E A 1 all over Jacobian squared, 1/4 minus 1/4 minus 1/4 and then 1/4. Yes? And then you have now your line integral dx. So we have to convert everything to C because we mapped it already. So what is C, by the way, or what is dx? We can use again your Jacobian. So what is the definition of your Jacobian? Jacobian is equal to dx d to c. So for J equal to dx dc, we can have your dx equal to the Jacobian dc. So getting close, almost there. So your K equal now to EA 1 all over A squared. And then we have now here 1/4 minus 1/4. Yes? And then we have now here the integral. So instead of a line, this one becomes a lambda. So don't worry about that. Because of our mapping. Sorry, I didn't show it earlier. So there you go. This one is a line integral, so we just put it a lambda. It's just a symbolic form. So we have this one to be J dc. Yes, so we have Jacobian cancel out 1 dc. So what is dc? So that is now EA, remove there 1 all over J. We're getting there. So what is the integral of dc? Integral will be C from C1 equal to minus 1 to C2 equal to positive 2. Yes? So this one goes out. The integral of BC is C from C1 to C2. So this is J. So what is the value of J earlier? Where were we? Ah, there you go. So this is the value of our J. J is L over 2. Yes? And then if you're going to have your C from C1 to C2, you have this one to be, that will be 1 minus a minus 1, that will be 2. Let's continue. Right. Okay. So we're there. This one is equal to 2. This one is L all over 2. So we have now here K equal to EA 1 L all over 2. And then we have now here 1/4 minus 1/4, 1/4, 1/4, and C is equal to 2. Right? This goes up. 2 multiplied by 2 is 4, divided by 4 is 1. So we get K equal to EA all over L, 1 minus 1 minus 1 and 1. Finally. Good? So the point here is that this one is a symbolic form, like I said. We can do the same for truss, we can do the same for beams, we can do for frames, but we cannot get a symbolic form for 2D elements. We cannot get the same thing for 2D elements. So what we're going to do to be able to get the values of your stiffness matrix, we have to integrate. Not the analytical integration, but the numerical integration. Okay, so just an example for 2D. So we have our strain displacement matrix, right? So this is your strain displacement matrix for plate. So how will your Jacobian look like? It's a matrix. So it's not just a single value. It's a matrix. Yes? So that's how your Jacobian will look like. So, what's important to know? So we're just here for a bar at the moment, so just for a bar. We have F equal to K multiplied by U. And then K, we were able to get this one using this equation, volume integral of your BE dt dV. Yes? And then your V is a derivative of your a function. this one will be a partial derivative with respect to x. Because we have x, y, z later. So anyway, this is just for a bar, so that's okay. And how do you determine your shape function? Of course, this will be coming from your displacement function. And u. So this is a very complicated solution. I can probably present you a more simpler solution later to be able to get this one here. So everything depends on your displacement. So what we did was we just took a linear displacement function. We determine your shape function, which are basically linear. Very simple. Shape function meaning n of that shape function is equal to 1 at the node of interest. That will be 0 at other nodes. Example, n1 at 1 is 1, n1 at 2 is equal to 0. So that's basically the definition of your shape function. So again, what also happened here is that we did a mapping. So if you have a mapping, then you have to have the presence of a Jacobian. Yes? So mapping is from, say, an x coordinate, xy coordinate, to a so-called C coordinate or C coordinate C1, C2. So this is still simple. The bar we had is just simple. So if you do this mapping, there will always be a presence of a Jacobian matrix or Jacobian variable for a 1D problem. So what was the method used to be able to derive this one? The method we used to be able to derive this one is method of weighted residual, where the weight is equal to the shape function. That is the Galerkin's method. Yes? There are many methods out there, and there are many simpler methods than this one, but because this one is very much related to what we have in the notes, then my focus will be looking into this similar derivation. But I will present to you a more simpler derivation later. But take note, this is just a bar. So as we go on, bar is like the simplest of all the elements. Spring, bar, and then as we go on, the derivation for this one becomes more complex. And take note, we're just looking at linear. If you're looking at quadratic, okay, to the second power, then it becomes more complex. So again, it's easy to use ANSYS or abacus, but the things behind that, yeah, it's really difficult. So that's what we want to do. We want to learn the background so that we can be a good user of these softwares. Okay? So thank you very much for your patience. I promise you more will come.